Alrighty everyone, welcome back. So in our previous video, we looked at feedback loops and the greenhouse effect and how those can impact climate change in a sense, or like making sure we have an understanding of what those concepts are. And I want to kind of break down the greenhouse effect just a little bit further, just to make sure that we all have a really good, awesome grasp on what's going on and like what the reasoning behind all of that is, and some evidence of current and modern climate change. Okay, and don't worry about this little situation as a dog scratch from last night. It was completely accidental, so I'm not trying to do my best Joker impression, so don't worry about that. Okay, so let's break down why this is all happening and essentially kind of the greenhouse effect or purposes of the greenhouse effect. So reminding ourselves about the structure of the atmosphere. This is not the first time we've seen this graphic, but I really want to emphasize that climate change is a tropospheric phenomenon. So what is happening down here in the troposphere? Not what's happening in the stratosphere, mesosphere, thermosphere, any of our other spheres. We're concentrating solely on the troposphere. And we know that the temperatures of our oceans and lower levels of the Earth's atmosphere are increasing. And I'll show evidence of that here in a bit. So what's going on? So just a basic retouch, perhaps, of electromagnetic waves and the electromagnetic spectrum. So in this case, wavelength refers to the length of the wave from the top of one wave to the top of the next wave. And frequency means how fast are those waves being received. So we call things long wave energy, meaning that it's cooler, it has a longer wavelength, lower frequency, lower energy, thus cooler. And those are the wavelengths that are leaving planet Earth, whereas short waves would be what we consider the sun's energy coming in. So it's higher energy, shorter wavelength, higher frequency, and warmer. So if we were to look at temperature and radiation, in this case, we have wavelength on the x-axis and energy on the y-axis. And there's two graphs here, the big one being energy from the sun, and the second one being energy from the earth. Really just, I encourage you really to take a pause on the video and make sure you study this graphic intently, and really just shining in on this idea that the sun is much, much, much warmer than the earth, and it's emitting much shorter wavelengths than the earth is. And also just keep in mind that the sun is giving us all different types of radiation, ultraviolet, visible, and infrared, whereas the earth is only emitting infrared radiation. And so, so this is showing the difference between those in that case. So what happens to solar radiation as it comes through our atmosphere? There's basically four main ways that energy interacts with our atmosphere. I know this says incoming solar radiation, but I do want to make sure that I want to emphasize that this is both for incoming and outgoing energy, as these bullet points will show. So basically we have one is transmission. So that's where radiation or energy passes through the atmosphere without interacting with any gases or particulates. It puts on its blinders and says, no, don't talk to me, don't look at me, don't even breathe on me. I'm just going straight through the atmosphere to the surface of the earth. No interactions with anybody. Whereas absorption can happen when that energy is absorbed either by an object or by molecules in the atmosphere or whatever, and then can change that object's temperature. And then the last two are reflection and scattering. And these two are pretty similar. Reflection being that energy bounces back from an object, whereas scattering is deflection by atoms, molecules, or aerosols. So reflection would be like reflection of light in a pool or off of ice or snow. If you do any sort of winter sports, then you know you got to put sunscreen on, even on the underneath your neck, because all of that radiation reflecting back can actually give you a sunburn. And then scattering is like why we see the sky as blue, right? So the composition of our atmosphere gives us the pretty blue skies that we see. If our atmosphere consisted of a different composition, then we would actually see the sky as a different color. or if you were around what I call Apocalypse Day, September 9th, 2020, when this whole sky turned orange because of a local fire. That is the sun's rays scattering through that smoke. And then what we see visually is that really strange red color. So what are the gases that are responsible, or sorry, I'm going to go back 1 second. So climate change and the greenhouse effect is all about this absorption and scattering sort of situation. And there's, if you were to look at like a breakdown of the various gases in the atmosphere and which absorb and reflect and scatter back different wavelengths, we would see that water vapor is actually number one. But then some other concerning gases are, of course, CO2 and methane. And that's simply because of the wavelengths that they reabsorb and scatter back to us. And so what are the gases that are responsible for this? Of course, we know about CO2, we know about methane, and nitrous oxide is also in this as well. We also have, of course, a concern that methane is trapped in some of the permafrost in the Arctic regions that will then seep out as that permafrost starts to thaw out. And of course, we've talked about methane in other instances when we talked about oil and natural gas extraction. So those are certainly cause for concern as well. And this graph here is looking at the last 2,000 years, or from 2005. If we were to look at something similar, CO2 would be super skyrocketed. And so it's really just important to note like the gases that are responsible for this, for the absorption of molecules. So again, they're acting as a blanket, retrapping that heat back in. And this graph here is of the Keeling curve. So this is observations of carbon dioxide in the atmosphere. This is taken from Hawaii, from Mauna Loa, which is the tallest peak on the Big Island of Hawaii. And I want you to consider why that location is primo for looking at CO2 concentrations in the Northern Hemisphere. But what I also want to point out, and I want to pull up, hopefully, maybe this website here that shows the Keeling curve. So what I like about this is, and I encourage you to check this out on your own, looking at 1 week, 1 month, if this wants to work, of course it's going to be silly, looks at 1 month, 6 months, 1 year, 2 years, the full record, which is what we were just looking at in the slides, 17,000 to present, or excuse me, 1700 to present, 2,000 years, 10,000 years, 800,000 years, and then a new tab, which they recently added, is 70 million years. So this looks at other different types of what we call proxy data, which you'll learn about later on. But we're getting a really good comprehensive analysis and idea of CO2 concentrations in our atmosphere a long time ago. So why does that matter? What sort of relationship can we get from CO2 and temperature? Well, the correlation is pretty right on the nose, right? So this is actually from one of my weather textbooks, but on top we have temperature conditions. The bottom we have CO2 concentration, and you can pretty much stack one on top of the other, and it's almost a perfect match. Something that I really want to point out though, and it's a little hard to see it in this particular graphic, but if you were to put like a piece of paper up over parts of this graph, like where you start to see a stark increase in CO2 versus temperature, you can see that, like if I'm gonna make an attempt at drawing a line here. It's a terrible line. But what I wanted to try and point out is that CO2 increases much or earlier than temperature increases. So that implies that the CO2 concentration increasing is what causes the temperature to increase, not temperature increasing causes CO2 to increase, the other way around, right? So some skeptics like to try to kind of paint the picture in that other way. Okay, so last few things I want to cover here is to kind of, in this video, just kind of zoom in just a little bit and look at what's going on now and kind of a little closer look here and just look at, some graphs. So we can see from this graphic here from NASA that global surface temperatures are rising. So this is looking both at land and ocean data. I encourage you to play around with this source here. You can make all different types of graphs. You can also download the data yourself and play around with it, make your own graphs if you so choose. But what we can see is a very clear increase of temperature all around the world, not just in one particular location. If you wanted to, though, there's another website where you can look at maps. So for me personally, maps are my go-to, mostly because I'm a very, very visual person, and so graphs are fine. I can understand graphs quite nicely, but I think maps can be like a little bit more easy for some folks to look at. So what we're looking at here are the last 2 decades, the annual global temperature anomaly. So anomaly simply means departure from the average. So of the annual temperature anomalies from 2000 to 2010 on the left and 2010 to 2020 on the right. And I encourage you to pause the video and play a little game of what do you see? What region do you see is warming faster? What region do you see, if any, are cooling off, in fact? And we do indeed see those. And even consider things like land v. water, that kind of stuff. So it's really quite fascinating. And again, you have the source information here where you can look into those ideas. And if we look at our 10 hottest years on record, are the last 10 years. We got 2014, 2015, 16, 17, 18, 19, 20, 1, 2, and 3. So the last decade has been the 10 hottest years in record. And these records started in 1850, I believe. So what are some things that we would expect to see from that, from these changes? And by the way, it's really important to look not just at temperature data, but also how things are responding in the natural world. So the next 3 slides here are looking at some graphs from your book, and I just wanted to bring them in here. I encourage you to look at them closer in the text or pause the video, but things that we would expect to occur. For example, if we're looking at ice melting, observation that ice is melting, we're also observing that sea levels are rising. I'll touch on that in another video. Changes in weather, that precipitation is changing. So extreme one-day precipitation events are increasing in the contiguous United States. And that means that species are also shifting where they are living, right? So if a species, a various species, in this case we're looking at a bird, it will follow the climate that it needs to live in, that kind of thing. And what's happening also is some species aren't able to adapt to some of these changes fast enough. So they then, are perhaps going endangered or maybe even extinct, things like that. So pretty wild. And lastly, some other things that we would expect, seasonal weather patterns are also changing. So looking at last spring frost, so when is the last frost day, and then the first fall frost, so that like later to earlier, and we can see that there's this shift happening, and that has a huge impact on flowering and any plants that rely on temperature in order to know when to flower. So if it gets too warm too quickly, they'll flower out, and then, oh shoot, here comes a frost event, and depending on the species of tree or plant, that can actually be very, very harmful for plants. I also recently listened to a podcast. I found a meteorology podcast recently, and a recent episode looked at how allergy seasons are shifting. And there is evidence out there that suggests that the allergy season is actually starting about 3 weeks earlier. But not ending earlier, so starting earlier. So things are getting warmer, things are starting to flower, and you're starting to get the sniffly, itchy eyes earlier. So it's actually not just you, it is something that is observable, which I think is quite wild. So In our following videos, we'll kind of dive a little bit further into these ideas and some of the various global impacts that can happen thanks to this lovely thing called climate change. Thanks so much for watching.